Welcome again in this big room again. We are going to have 5 lightning talks now, and then right straight to the after party. So our first lightning talk speaker is Krzysztof Wende. Please welcome Krzysztof.
Hello, so I want to talk about developing Elixir with Atom. So at first I will make some survey. How many of you are developing actively Elixir? Okay, how many of you has considered developing Elixir? That's great. Okay, so right now for active developers, what tools are you using? I guess most of you are using Emacs. Who is using Emacs? Not so many. Vim? Really? Okay, no worse. Sublime. Okay, quite few. And who did use Atom for? Just one? No? 2 people. Okay, so it's quite good. So I'm the creator of Atom Autocomplete Elixir plugin. And I would like to show you that because right now, I've checked all of the plugins, and right now Atom is most suitable, it has most features to develop Elixir in. I know some of you probably are religious about Emacs or Vim. I'm using Emacs myself, so I know that kind of stuff. Emacs right now is missing few features, like you can't have really syntax checking in Elixir. You can't have underlining of errors and warnings, which Atom right now actually has. And all of you know that some of those editors has their flaws. Emacs is really hard to learn. Vim is not a full-fledged IDE. Sublime is not open source. So there's also IntelliJ IDEA, which I know how many of you are using IntelliJ IDEA for Elixir. That plugin actually pretty sucks right now. But I guess they will develop it. So I would want to show you what can you do with my plugin right now in Atom. So if I put it here, right now you can, you've got intelligent autocompletion of all models. Is it all right in here? You can see the functions of each model. You can see the array of functions. You can see returned types of all the functions. You can see taken types of the arguments, which is pretty nice. You can also expand all the snippets. Yeah, it's hard to use with one hand. And like I said, it has error checking, which is pretty good because it's missing in most of the editors. You've got all the errors of the compilation in here. And the Elixir community is growing. Atom is also pretty popular editor. It's getting much more popular. So I guess it's worth trying, especially for people not really knowing more advanced editors like Emacs and Vim. So I invite you to check it out. And to finish, I would like to brag with some numbers. Right now, 1 week ago, this plugin hit 10,000 downloads, which makes it 3rd most popular tool for Elixir, 1,000 less than Emacs plugin, the Alchemist, and only 3,000 less than IntelliJ IDEA plugin. And it's twice the number of Vim plugin. So thank you for your attention.
Thank you. Now we would like to welcome Mach. Okay, thank you. With a talk about object-oriented programming in Elixir.
All right, so my name is Vitek, and I'd like to talk about object-oriented programming in Elixir. And before doing that, let's take a look at some example Elixir code. So here we just have a module and with a name field And on the bottom, you can see how we can interact with it. And we can also define a function, say hello to, that accepts just 2 arguments. And when we pass in Joe and Robert, it would output hello Robert, which I always wanted to say. All right, so now that we have basics, here we can just see some simple modules and functions and immutable data that we pass around. So let's make some mess. Let's do some OOP. So I wrote a library called OOP, and this is how you can use it. So you import the OOP module, and now you can start to define classes in Elixir. So you can have a name field here as well, and you can instantiate objects of these classes, and you can call methods on these objects, as you would expect. And you can also define methods on these classes. So we have the say hello to again, but now it only accepts 1 argument. And there is a this keyword because that's what you would expect in OOP language. And finally, we have mutation. That's something that you often have as well in an OOP language. Okay, so perhaps you are wondering, well, how does it work? This is all valid Elixir code, which also means it compiles to Beam, which can run everywhere Erlang runs. So how does it work? The answer is, you don't want to know. And the real answer is, it uses macros pretty heavily. Okay, well, so maybe that's not that bad, all that I showed you. Maybe it's not that bad, so what's worse? So what's worse than OOP? And my answer is, it's OOP with inheritance. And this library supports that as well. So we maybe have a human, and maybe there's a doctor with a name, and we can do what you would expect. Okay, so maybe that's still not that bad. So what's worse than OOP with inheritance? Yes. Yes, so this library supports multiple inheritance. So again, maybe we have a human class, and we have a spider class. So maybe we want to have a Spider-Man, which inherits from a human and spider. And yeah, you can have as many classes as you want. You may run into some interesting diamond problems and such. Okay, so a couple of guidelines. Perhaps you have heard some of them. So what's the first rule of writing macros? As I mentioned, it uses macros. The first rule is don't write macros. So I'd like to propose a new rule, which is, what's the first rule of doing OOP in Elixir? And don't do OOP in Elixir. Okay, so maybe you are wondering, well, I wrote this library and I just told you not to use it, so what's the deal? So the reason is that I wrote it is that I wanted to show you how powerful Elixir is, that you can, with macros and some other facilities, you can create some DSLs and abstractions and new semantics. That's also true for many other programming languages. But with these constructs, you increase complexity and you make your systems harder to understand and to maintain. Instead, we should strive for simplicity. And for those, just modules and functions are usually all you need. Thank you.
Hello, my name is Peter and I will show you something completely different from anything you have ever done with your computers. It's quantum computing. And I'm not sure if I can show you anything you and I will understand. And I'm not sure is the most important phrase you have I will use today. Oh. Okay. With normal computers, everything you write, your fancy objects, functions, macros, etc., are basically sets of bits, zeros and ones. But if I have quantum computer, every bit, let's say qubit, is not either 0 or 1, because it can be 0 and 1 in the same time. It's important that we could check that our qubits are, let's say, with a 0 with 40% probability, or 50% probability. What does it mean? It means that we could conduct our computation on all possible values at once. Let's say we could store in qubit two values, either 0 or 1, and then we can pass this qubit to a gate. Gate, it's quite simple, simple thing. Let's say it's something like that, and this will be in negation. Okay, we could pass there a qubit and get another qubit. If it will be a classic negation, we pass 0 and get 1, we pass 1 and get 0. If we have qubits, we can two values, let's say alpha and beta, and there are probabilities of 0 and 1. Let's say in percent. What we could get after negation? If we had 60% chance for 0, then after negation we could get 1 with 60% probability. And with 40% probability we could get 0. Okay. Why we do that? Yeah.
Actually, we can't.
Yeah, it's quite stupid example, but we could do something more. Let's say we could do quantum circuit. We could compose gates into circuits, and we could create something that adds two numbers. And I did something like that. If I would like to add two numbers encoded in 6 bits each, I run out of RAM, 8 gigabytes of RAM, so it's quite hard to implement and compute. But if we do that in quantum way, we could add all possible 6-bit numbers at once. So here, we could negate either 0 and 1 at once. But there is another problem. We should check what we get. In real quantum computers, we cannot tell, okay, we have 0 and 1 at once in the same moment with some probabilities. We cannot measure these probabilities, so we could spoil this one and say, okay, it's 0. But why? I'm not sure. But if we conduct some computation 10 times or 100 times, we could get results, let's say, similar to these probabilities. What could we achieve with that? We could crack RSA. This is a famous example that if we could conduct as many computations at once and check, let's say, which number is prime, we could find out quite fast how to get to our mailbox. Okay, but it's not real quantum computer. It's something I write to my university subject in Python, and it's horribly slow. But what's important, I could use it not in the... Okay, I could show in this library computation in that way it is described in papers. There's another problem. Let's say I implemented quantum Fourier transform. There was 3 papers. Each of them describes other algorithm, and I had to guess which one should I use. And I'm not sure, but I think I used the proper one. And okay, there is no time. Yeah. Okay. I show you this code because I'm not able to write all of it myself. So I hope somebody will help me with it. It's fun. It's very funny, but frustrated also. So maybe someone would like to help me.
So my name is Kuba, and I'm gonna tell you also about quantum computing, but from a bit different perspective, because what's a qubit? Ain't nobody got time for that. We're not gonna talk about it, but I'm gonna tell you just the very basics. So just like Peter said before me, classical bits can be 0 or 1 at the same time, which isn't kind of revelation. Now, qubits are like Schrödinger's cats, which means they're both dead and alive at the same time. And also, that doesn't probably give you much. But if you think about it, if you had like a string of n classical bits, you can only represent a single n-bit number, right? Well, it doesn't surprise anyone, at least it shouldn't. But if you have n qubits, and every single one of them is both 0 and 1, it means that in some way, some magical way, we describe 2 to the power of n numbers at the same time. But who'd care about that? Why should it interest you? Well, what if I tell you that we could, or we should, efficiently do integer factorization to break RSA or any other stuff, or minimize global functions, which means we could train like huge neural networks and simulate human brains, probably, or simulate social processes and actually send help somewhere before it's actually necessary out there because we simulated it before. Or if we could simulate complex biological systems like folding of the protein and all that stuff to find cancer cures and all that stuff. And finally, simulate quantum systems, because our world is all quantum physics, whether you like it or not, and we would like to simulate that thing. But even with the most powerful computers we have today, it's like, nah, it's just not gonna happen. No, well, we're not gonna do it. But if we have quantum computing, yes, we can do all of that. So basically, when I tell most people what I do with quantum computing, it's like, I don't really know what is that. Well, for real quantum computing, or at least the way we see it scientifically, is pretty simple, and it's like that. So it's probably not the most sexy thing you can think about, but at the same time, it's like a function, and it's really easy to represent it using functional dependencies. This is another way of describing it, and if you think about it, like every line represents a single qubit, and you have only like transformations applied to every one of those. And while it may not appear like directly easy to you, we have 2 ways of writing that kind of stuff into real computers. Write a machine language, good luck with that, or we can just use any functional language we have today to describe those proper functional dependencies of qubits to program a real quantum computer. Now, why should you still care about that? Well, just because functional programming languages are the future of quantum computing. If we ever gonna have it, then functional languages are gonna be the languages of quantum computing, which is gonna be so super powerful and cool. Unfortunately, building a real quantum computer is like another story, and it's quite far from today. The good news is that there's a huge amount of research on it. Even if you never heard about it, it's like many companies, including Microsoft and Google and NASA and American government and all that stuff, putting just huge amounts of money into quantum computing, mostly because they would like to break the RSA, but there are other cool usages that I can think about. And it's kind of worth it. We could do so many cool things, not only like break the RSA, but we could really improve the world if we had quantum computing. So, is that all? Well, damn no. There's a lot to talk about. You really would need to understand the complex math behind it probably to start your, well, stuff dealing with quantum computing, but hopefully it's going to be much easier in the future. Just like today, you don't need to understand how electrons fly inside of your processor to write code, right? But as I am running out of time, I would like to thank you all for your patience, invite you to my GitHub if you're interested in any like theoretical and practical things about how to build a quantum computer, if I can say that. You can find it all on my GitHub and yell at me at Twitter. And that's all. Thank you very much for your time.